Well, hey y'all, I am off with little Gramster this morning, so you guys have digital me, and I'm going to bypass a little bit of the notes. Disappointment though, because that first page, see that pinched loaf of French bread on the front page? Gotta love that analogy on there. So if only I had some time, I'd dive into that. You know how excited I'd get about that. But the next thing is, if you skip over to, I think it's like page 2 in those volume notes, I think it's a 6.3 volumes, you'll see this problem. And this is a great one to give you kind of a reminder of how we go about doing volume. So volume is three-dimensional, and the whole thing in the first page, what it's getting at is that if you take volume, you want to reconsider how you think of it. Like when we did, if you do like a rectangular prism, so I draw one here real fast and I do volume, you guys all know it's length times width times height, and most of us just kind of memorize that kind of thing. But what's actually happening, the length times width part, so length times width times height, that part of it is actually what we'd think of as the area of the base. And if you think of that as how all volumes of regular figures are, if there's a consistent shape kind of going up, it actually doesn't even have to be consistent. But what you'd think of as the area of the base, I'm going to draw the full dimensions in there, times the height is actually how we go about getting volume. Then you have a more robust definition that really helps you understand some of these area formulas or volume formulas that we have for integration. So the first one, that 4/3 pi r cubed business, let's go ahead and do that one. I'll make a new page, I have lots of room. But okay, so what it looks like is 4/3 pi r cubed, and that's the volume of a sphere. And most of us remember that one, but we're going to get there a little bit differently and then just use a method that you all might remember. That's the disk method. So 4/3 pi r cubed. So I'm just getting the stage set for you. What you can do to get that instead is if you take the formula for a circle, and you guys may or may not remember this from last year, but you kind of memorized them. Do you remember that like x squared plus y squared equals r squared is the formula for a circle? And I think even for the AP Calc 1 exam, it's something to memorize, and that means for this class it'd probably be good too. If you plan to take the exam, it's a good thing to know. If not, then you'll just distant memory is good enough. Where r and negative r are, you know, the radii, the places where the circle touches on those axes. And if I want to get the volume of this, you take this, basically I think of it in terms of taking a flap of function and rotating it in some way. And you can kind of do a couple different ways, but I like this analogy that when you guys do volume, it's akin to the formula for the disk method. Like if we want to get the area of a circle, sorry, I know I'm going back and forth between area and volume, but there's a big point here. The area of a circle is pi r squared, and what happens is, it seems to me that when you take and square r and take it times pi, it enacts kind of sweeping around this radius around the circle, and so it swipes out the circle. So it's kind of like if you're sitting on the ground and you sweep a stick of this radius on the ground and you spin it around and keeping the center consistent, it'll sweep out this circle. And so when I do volume, it's kind of a similar process, interestingly enough. If I can just get the region of this flap, the function that represents it, and we can, if you solve for y, and this, and only do the top half of it, so maintaining its function form, you get the square root of r squared minus x squared. That's going to be the formula for that top half that I've shaded over there. So that's, if I integrate that, we're going to get area, right? R squared minus x squared dx. But if I want to get the volume and I want to spin this thing around, I do like I did for my radius down in that previous problem right there. I'm going to square it and take it times pi. So if I square this thing, so square and take it times pi, that gives me the volume of rotating this little half circle around that x-axis. So we're just going to spin it around, right? Take that thing and spin it. And you've seen this before. You guys have done rotational volumes a little bit. But this act of squaring it and times pi, even within the integral, spins it around the x-axis, kind of like the radius got spun around on a center and created the circle area. We're going to do a whole flap, a 2D flap, spun around the axis creates the sphere. And if we actually do the calculations on it from negative r to r, we've got ourselves, we're going to get 4/3 pi r cubed. So that's worth a little adventure. So I'm going to put this all back together. So if you can follow along here, let's do this thing. If I square the square root in that function, of course now we're left with just pi from negative r to r. And we just have r squared minus x squared dx. And this is a good time to remind you that we're integrating with respect to dx. And that means these are x values on the integrand, top and bottom. What's going to happen is that means when I get to r, I think of that as a constant because it's not an x. So you treat it as though it's a constant. Now I'm making it is a constant if I actually put a radius value in there, but even I could leave it r and just leave it blank because I want to, and I want r to be part of my expression when I'm done. But now it's going to be a constant because this is integrating with respect to x. So let's do this thing. So if that's a constant, then the antiderivative is going to be r squared is just going to be r squared x. That's going to be the first part, so let me get down here, r squared x, because that's just integrating a constant. And then, of course, it's 1/3 x cubed. Bingo. And we're going from negative r to r. That's the antiderivative, and you can kind of see the light at the end of the tunnel. We're going to plug those in. And sorry, it's getting a little squishy in here, but imagine I'm just going to take this down here to the bottom. I'm going to expand this out. So I got pi. And now let's plug our stuff in. Let's put the upper bound in there. And then let's put the lower bound in there, and we're going to subtract them. And we got this thing. Okay, hanging in there. So upper bound would be r going in. That would be r. I'm just going to do a little highlighting here. Let's choose a different highlighter color so you can see it better. Let's do green. But I'm going to put it in for x. R goes in. We get r cubed. And if I put it in and the other one, it's minus 1/3 r cubed. Right, I think. You guys can make fun of me if I do something wrong. There you go, r cubed, and we put negative r on the other one, so negative r times r squared. There is a little bit of a conundrum there. It is the regular r squared that's part of the expression, and then I'm putting negative r into that, so it is going to be negative r cubed. Ooh, some weirdness in there. And then minus 1/3. And we're going to do negative r cubed, which is a negative to an odd power is going to be negative itself. So we're going to end up with positive 1/3, or r cubed over 3. Bingo. So all that, now here's the math magic. It's all going to simplify to 4/3 pi r cubed. And there's a little bit of distribution and other fun things taking place. Big hints, of course, is that we probably ought to combine these. So I might call this 3/3 r cubed, so that I can subtract 1/3 r cubed in that first one. And then same thing in the other one. I might call this negative 3/3 r cubed. And so if you can see on the first one, we take, this would be, what, 2/3 r cubed? Sorry, it's getting a little squishy and it's down at the bottom. There's a pi. And then over here, it's going to be negative r cubed plus r. So it's negative minus a negative 2/3 r cubed, and of course a pi. I'll squeeze it in there. How about that? So that minus a negative, we're going to end up as a plus. And if I got 2/3 r cubed plus pi times 2/3 r cubed plus another pi times 2/3 r cubed, we get 4/3 pi r cubed. And if you can buy that, then you got your original formula. So the cool thing is we know that formula. We have the disk method, which justifies it. And that's just a little reminder, the disk method. Disk method is for functions that are flush against the axis of rotation and there's no gap between it. So the next thing I want to do is give you guys a little disk method refresher. And then I'm going to have another video of you guys introduced to what's called I'll let you just check it out for yourself. It's good stuff. Okay, so hang tight. So with this, I think I said disk. I meant washer. You remember washer method. Washer is the one that has some kind of gap in the middle of it. So between your axis and the rotational axis and the function itself. Now, you're going to think, for some of you, you just don't remember this stuff because I know how it goes in Calc 1. It just kind of is the last thing that you do, and you kind of get a mild understanding of it. So think of this as the overarching introduction, and then of course I'll pick up the pieces tomorrow. And some of you just remember it and really love this stuff, so just hang in there. Little differences of experience with this, that's for sure. Now, if I do cosine and sine, and I think it says it was rotated about the x-axis to form a solid. All right, here's cosine, right? And then here's sine, and I'm just doing this real rough. So, and this one will peak when that one hits the bottom. There's my sine curve. And I think it says in quadrant, in the first quadrant. So if I just give you a little bit of that, you're going to see there's a little fin sticking up there. Finn. I remember that was one of the popular names when Nora was born. If we were going to have a boy, we might have named him Finn. Isn't that cute? So here it is. The fin there, and I think I'm supposed to rotate it about the x-axis where you can see that there's kind of this gap zone right in here. I'm going to get rid of that. But that gap between the x-axis and the function is what requires that there's going to be a washer. Okay, yeah, sorry for the background announcement there. Now, as I rotate this around, let me give you a little visual, just in case you're not the rotational visual type, but that just spins around the x-axis. Now, I wish I had my computer software going where you can do those rotations, but it's really fun. I might get you guys onto that here a little bit later. But I'm going to spin that around and calculate the volume of that object. Kind of looks like me, like somebody like gouged out the top of a Hershey's Kiss with like a spoon or something. They're going to dig a piece of that out, and then it'll be sideways. The volume piece usually goes pretty smoothly for these. I mean, the integration, once you learn how to set them up, it's just knowing which method to choose down the road that starts to get a little bit hairy. Now you guys have the formula up above, and the way it works is you do outer radius squared minus inner radius squared, and the deal is it's like I am rotating. I'm going to do some multicolors going on here, so watch with me. If I spin, and it's that top piece, if I spin it around the axis right now, the outer function, if I spin it, I'm spinning this whole flap, and so I'm going to get this whole solid piece here if I spin that around, okay? That's the whole outer radius squared, and I'm going to have a pi in there, okay? So I'm going to put pi, I'm going to put outer radius of x, and if I wanted just that volume, I'd go outer radius squared, like that. But I'm not doing that. What I'm actually doing is I'm doing that, and then I'm coming back in, and I am carving out the inside. This is me digging the spoon in and spinning this piece, this blue chunk right here. I'm spinning that flap, and what it does is it carves out the inside here. It makes like a little bowl inside there. And I hope this drawing gives it some justice. Sometimes my 3D stinks, so just hang in there. That is me taking from the green, I'm carving out that blue stuff in the inside. Okay, and the way we take things out, remove them mathematically, of course, is by subtraction. And so the formula is really saying, if I go up there, it's outer radius squared minus inner radius squared is me doing the volume of the outer one, and then I'm doing the volume of the inner one that I'm taking out of this. So that's the long and short of that method, is you're taking the outside and then carving out the inside. And of course there's a pi in there because they're both being spun. So think of it as like two integrals. Do the volume of the outer piece and the volume of the inner piece, and when I cut the inside out, it leaves kind of a gap in the middle. And in the integration techniques, you guys are champs. So those are the two methods. Then I have this new method called the shell method, and I got a video for that you can watch and get completely confused by, and then I'll try and help you out tomorrow. So do your best and tackle what you can.